But our ring isn't going to accept electrons very well. So in any reaction where we are reacting benzene with a nucleophile, we need a leaving group. And we looked at our nucleophilic aromatic substitution, and not only do we need a leaving group for that reaction to occur, but we also need an electron withdrawing group, ortho or para, to the leaving group. Otherwise, we cannot stabilize the negatively charged intermediate enough to allow the reaction to occur. So we're going to look a little bit further at that here by looking at this example. So we have a nucleophile. Hydroxide has a accessible pair of electrons, and chlorine's a good leaving group. But we won't get any reaction at our typical small temperatures because we don't have an electron withdrawing group in the ortho para position. Now, if we increase the temperature, now first off, let's think relative terms. What's room temperature in Celsius? About 27. It's about 27. So 25 to 27 is room temperature in Celsius. This is 350 degrees. That's really, really, really hot. So these are not easy conditions. Most compounds will degrade at this high temperature. And benzene can stay intact, but you have to watch your solvent, of course. This is way higher than most solvent conditions. But we can force a reaction to occur. Again, just like our nucleophilic aromatic substitution, notice that we do have a loss of the leaving group. That's not the case in electrophilic aromatic substitution. So we do still have a loss of a good leaving group. We still need a good leaving group. Nucleophile will not react with a benzene ring that doesn't have a leaving group. So unsubstituted benzene, we won't get any reaction. If we use a stronger nucleophile like NH2-, you know that's a really strong nucleophile, we actually can get this reaction to occur at slightly lower temperatures. And again, the conditions are still harsh, but in this case, the conditions are harsh because NH2- is really harsh. And remember, in both cases, we can't mix our strong base with water because that would just react with our strong base. We wouldn't get any reaction with the benzene ring. So what reaction is this? And it turns out the mechanism is a lot different than the nucleophilic aromatic substitution. And we're actually going to see an intermediate that is surprising for this example based on everything that we've learned so far about stability. So we're going to look at that in more detail. But NH2 is stronger of a nucleophile. So to understand the mechanism, if we look at a substituted benzene substituted with something like a CH3 group, now we can't have a very strong electron donating group. It will make this reaction really slow, but CH3 isn't a huge electron donating group. But what we actually see when we have substitution is that not only do we get the expected product where we have the substitution occurring where the leaving group is, but we actually get an additional product where we get the substitution occurring at the adjacent carbon. Now, also notice we still do not have the leaving group. The leaving group still has to leave both of these. So what reaction does, or what mechanism does these data point to? So the mechanism this data points to is a little bit different than a mechanism that you would expect because of the regioselectivity. If it was just going through the mechanism that's very similar to our nucleophilic aromatic substitution, where we have our negative charge stabilized around the ring, we would only expect the reaction to occur where the leaving group is. So this has to be a different mechanism. Isotopic labeling can somehow help with assessing a mechanism in the lab. Now, all the mechanisms I show you, we can come up with a mechanism that makes sense. But to actually understand if that is the correct mechanism that is going through 99% of the time, you have to do experimentation. These mechanisms that I teach you in class are not just taught because I came up with them. They're told to you because of experimentation that's been done by many chemists before you to actually understand if that mechanism is the mechanism. Sometimes we use kinetics. We've looked at that a little bit with SN1 and SN2 reactions. In this case, this mechanism was really looked at by isotopic labeling. So what isotopic labeling is, if we take one of the carbons in the benzene ring but replace it with carbon 14, we can follow that particular carbon with characterization methods. Because it's going to have a different NMR shift because it's carbon 14 and not our typical carbon 12. So that's what we call isotopic labeling, and that's represented by the star. And with isotopic labeling, it was found that you got 50% of the reaction occurring at where the isotope was labeled, where the leaving group was, and 50% at the adjacent carbon. So this suggests, again, a different mechanism than NAS. So the proposed mechanism is that our nucleophile, in both cases, either NH2- or our OH- conditions, can act as a base. So it deprotonates a hydrogen, and then that forms a negative charge on the carbon. That's our sp2 carbon. Now that's fine because that sp2 carbon is a bit shorter, remember acidity, so that is a little bit more of an acidic hydrogen. But then that lone pair can form a pi bond between these two carbons, making our leaving group leave. Now this is a surprising intermediate because it's a triple bond, but notice the geometry of it. We typically will always say a triple bond is always going to be linear. But this triple bond is not linear. This triple bond is going to have an angle because of the ring. So this is a really, really unstable intermediate, and it is surprising. Now one thing to note, is this compound still aromatic? Yes, still aromatic. There's only 6 pi electrons that are conjugated. The second pi bond of the triple bond is not in the same plane. Remember, your unhybridized p orbitals are not in the same plane. On one carbon, one will be up and down. The next p orbital would have to be either x, that would be x, or z. It doesn't really matter which one. So if all of these are y, meaning up and down in their conjugation, this second pi bond can't be in conjugation with those. So you still have a 6 pi aromatic system. The second pi bond is isolated to those between those two carbons because no other pi bond is in the Z range. So remember that. So this is still aromatic. That holds some stability to the compound, but the bending out of the correct geometry is going to make it pretty unstable. Which actually explains why when doing this with hydroxide, you have to use really, really, really harsh temperatures. Because otherwise you wouldn't be able to get over the activation energy. When using NH2-, it's so reactive that it can force this to happen. But this does explain our regiochemistry because of this triple bond. So we call this the benzene intermediate. And we only see this benzene intermediate at really high temperatures with sodium hydroxide, or when we use NH2- and we don't have an electron withdrawing group, ortho or para to our chlorine. We do have an electron withdrawing group, ortho or para to our chlorine. The nucleophilic aromatic substitution mechanism is just easier. It's a lower activation energy, so it's likely to go through that instead. But without the electron withdrawing group, we see this reaction. So the benzene is short-lived. It's really unstable. It's an intermediate. There's no way to isolate it. Though I will show you an experiment that proved that it does exist. So we'll talk about that in a second. But we do have a 6-membered ring. We do have our hybridized carbon. But it is still aromatic because that second pi bond is not in the same plane as our aromatic ring. So you can think about it as either the triple bond or as two radicals next to each other. And based on modeling, mathematical calculations, and experimentation, it's likely that it's existing as a hybrid of these two forms. It's likely not either one form or the other form, just because of stability. And again, what's really doing that is the fact that we don't have really good overlap because it's not linear. So the next step in the mechanism is now our nucleophile, whether it's OH- or NH2-, is going to attack, and it can attack either carbon of the benzene, either the carbon where the leaving group originally was, or the adjacent carbon. So that pushes the lone pair back on this carbon, and then either we work up the reaction by adding an acid at the end, or if we're using NH2 minus, ammonium liquid could be a source of H plus. So usually that's mixed in with the reaction. So then we get both products. Now, if you only have one substitution on the benzene, this is only showing the possibility for 2 products. You actually have the possibility for 3 products, because remember, your ring is in resonance where our double bonds are considered between all of the carbons. So while I'm showing the benzene existing between this carbon and carbon 1, I could just as easily, and it's going to happen because it's the same compound, just as easily have our benzene between carbon 1 and 5. So my NH2 group can be on carbon 1, carbon 2, or carbon 5, because my benzene can be here because this, remember, this double bond, this is in resonance. So if I drew that, my NH2 on carbon 5, here's my star. I don't know why doing that does anything. The reason why I'm not showing you both pathways is because these 2 things are the same. But depending on the R groups that are attached to the ring, these 2 things might not be the same. So you have to consider it. So you have the possibility of 3 products, but in this case, 2 of them are the same product. So I'm not showing you different. NH2 minus is not a catalyst, however, because it is being used up in the mechanism. So it's not a base catalyzed reaction, but it is going through basic conditions. But it's not catalyzed. A definition of a catalyst is that it's reformed throughout the reaction. We're not reforming NH minus. We are completely using NH minus. So keep that in mind. We are using parts of NH minus. So technically, you need 2 equivalents there. So again, I said that I'm going to show you with the chemical reaction that the benzene does exist. It turns out that if you make that benzene form, and then you throw in a dienophile, you can actually get a Diels-Alder reaction to occur. And the only way a Diels-Alder reaction would occur is if you actually had that benzene intermediate. So if we throw in something like furan, a diene, which a really reactive diene, like furan. So remember, here the diene is very reactive because it's holding that S-cis conformation. If we didn't have the benzene present, then no reaction would occur. But with the benzene present, we actually get this cycloadduct, where we get the Diels-Alder reaction occurring. So this really suggests that the benzene forms. Because if the benzene high intermediate wasn't forming, we wouldn't get this possible product. So we could actually trap the benzene and react it. Now we can't isolate the benzene. We can't really do any specific characterization to show the benzene is there because it's there for such a small amount of time. So this was the best chemical reaction to show that it existed by reacting it while it existed. So basically, you are putting this all together, and again, if this doesn't exist, nothing will react with this. So that shows that benzene is an intermediate. And that's really the only way you can see it. You can't really do any characterization. You can't isolate it. It's too unstable. So how do you determine what reaction you're going to get for these 3 reactions we've talked about? Electrophilic aromatic substitution. Well, actually, before I do that, I want to talk a bit about what I was talking about here. So if we start with, it doesn't matter. If we start with, let's say, here's our leaving group, and we're not starting with the para, but this is in the meta position, then we actually will get 3 different products. where our nucleophile is going to be on carbons 1, 2, and 6. And it's really not something where you can say one's going to be major. You're going to pretty much get a mixture of all three in roughly the same amounts, unless if for some reason sterics is really keeping the reaction occurring at 2. Otherwise, you're likely to get all three products. So if we react this, and remember, this could be NaNH2. You might see that. I'm just showing it with the negative charge. So our intermediate that we're going to get here is our benzyne here, or we can also get, not or, and, because it's not an or thing, and we can get our benzyne in this position. When I get lower on the page, it's not calibrated as well. So, of course, at carbon 1, both of those intermediates can form carbon 1. So we will get the NH2 at carbon 1, but we can also get the NH2 at carbon 2. And we can get the nucleophile at carbon 5. Because we started out with an asymmetric compound. So you do have to watch out for that with enzyme. With our nucleophilic aromatic substitution, the substitution only occurs where the leaving group is. But with this one, we have to consider that we have the possibility of 3 possible products if we have any substitution on that ring that will represent 3 different products. And this would be 3 different products. Here, the methyl is ortho to the NH2. Here, the methyl is meta. And here, the methyl is para. That's 3 different compounds. They would have 3 different names, so you would have to represent. And unless if there's a lot of reasons for this place to be blocked by sterics, and there's not really, then you would get all 3. So the reason why we only showed 2 in the other case, because the 2 possible other products were the same. So these 2 are the same. But technically they both exist, we just don't see any difference with them because they're the same compound. So how do we determine of the 3 reactions? So first off, look at your reagents. Are your reagents nucleophiles or electrophiles? Do your reagents have a positive charge? Are they going to accept electrons, or do your reagents have lone pairs that can donate electrons as a nucleophile? That's your first step. If they are electrophiles, then you're going through electrophilic aromatic substitution, and remember, the substitution can only occur at a position that has a hydrogen. And goes through a carbocation intermediate, your benzene ring is acting as a nucleophile. If you look at your reagents and they are nucleophiles, the most common we talk about is OH negative or NH2 negative, but it could be OR negative. It could be sulfur. It would be a nucleophile. So depending on what you're reacting. If your reagent is a nucleophile, then you may be going through nucleophilic aromatic substitution. You may not get a reaction, or you may be going through the benzyme reaction. So the 3 criteria you need for nucleophilic aromatic substitution is a leaving group, a nucleophile, of course, and an electron withdrawing group, ortho or para, to the leaving group. Then your substitution is going to occur at the carbon of the leaving group. If it doesn't contain all 3 of those, then it may be going through elimination addition if there's strong enough conditions. If it's OH, you have to have very high heat. If there's no high heat, you won't get a reaction. Or, if you have a ring and it doesn't have a leaving group, it's not going to go through either. It doesn't matter what nucleophile you're reacting to. So you have to have a leaving group in both cases. Even if we're talking about NH2 minus, if we have an electron withdrawing group, ortho or para to the leaving group, it's likely to still go through elimination addition because that's a lower energy transition state. It's only when we don't have that electron withdrawing group that it will go through that higher energy transition state of the benzene. So even though we don't need as much temperature to do the benzene with NH2 minus, it still won't go through elimination addition if it has a lower energy pathway available to it. Or at least it won't do very much of elimination addition. In both cases, if you're reacting with a nucleophile, you need a good leaving group. None of these reactions will occur without a good leaving group. So let's look at an example. And we're looking at this one, we're trying to figure out the mechanism. What's the mechanism? First thing you're going to look at is the reagents. We have sodium hydroxide and heat. Is sodium hydroxide an electrophile or a nucleophile? Nucleophile, it's OH negative. It has available electrons, it wants to give it up. So then our next question is, well, first off, notice it says heat, it's not specifying high heat, so it's unlikely to be going through benzene. 350 degrees Celsius is really high heat, you would specify that. The next thing is it going through a nucleophilic aromatic substitution? And what we have to do is find our leaving group. Do we have a leaving group? Yes. Then, do we have an electron withdrawing group, ortho or para, to that leaving group? Yes, NO2 is an electron withdrawing group, and it is ortho to the leaving group. So, this is going through our nucleophilic aromatic substitution, and the substitution is going to occur only at the carbon where the leaving group is. I could have multiple chlorines on this ring, but only the reaction will only occur at the chlorine that has the electron withdrawing group ortho or para to it. So you have to have that for the transition state to be low enough, because it's going through that carbanion intermediate. So it's a nucleophile. It rules out electrophilic aromatic substitution. We do follow our 3 criteria, so it is. Oh, and sometimes you see it. Nucleophilic aromatic substitution is written as SNAR. SN for substitution, AR for aromatic. Well, SN for nucleophilic substitution, and then AR for aromatic. So it is different from our SN1 and SN2. This is SNAR, specifying that it's a substitution occurring at an aromatic rate. But it's a lot different of a mechanism. So sometimes you see it specified as SNAR, like that. So our mechanism, our hydroxide attacks that pushes electrons to the ring to make our carbanion. And then this is just showing our most stable Meisenhower complex, but of course we have our resonance structures where the negative charge is pushed around, and you should know how to draw that. And then finally, we reform the aromatic ring, pushing out the leaving group. Now this mechanism is a lot different from our benzene mechanism, from our elimination addition. So you need to know the difference between those two mechanisms and be able to draw them. But this one would go through elimination addition because this would be a lower energy transition state. So that's it for our benzene reactions. Now we're going to take a bit of a jump and change. We've done 3 chapters of conjugated double bonds, but now we're going to go back and look at carbon-oxygen double bonds. A lot in this chapter is things we've already done. We've already done a lot with carbon-oxygen double bonds. Ketones specifically and aldehydes. We're going to save carboxylic acids and their derivatives for the next 2 chapters. But here we're going to focus, this is a pretty short chapter too, because ketones and aldehydes do some reactions, but they're not that effective. We've already looked at some reactions of ketones and aldehydes. We've reduced them. We've reacted them with things like the Grignard. So we've looked at some reactions. We're going to dissect this functional group more, look at other possible reactions they go through, but we're going to see a lot of the same things that we've already seen with these particular reactions. So first off, our aldehyde is our carbonyl that has a hydrogen attached, at least one. Our ketone doesn't have a hydrogen, we have 2 R groups. The simplest aldehyde is formaldehyde and has 2 hydrogens attached. If an aldehyde has a hydrogen attached, notice it always has to be at the end of the chain, because one's an R group, the other thing has to be a hydrogen. So that, of course, we'll talk about So we haven't really talked about naming these things yet. So the carbonyl group in pink is common to both. You might sometimes hear it called a carbonyl, a carbonyl. So that's our CO. And of course, when we did the acylation, you might hear it described as an acyl group. So note all those terms. It's very important in the synthesis of many pharmaceuticals. It does somewhat impart biocompatibility, not as much as carboxylic acids and esters. But we do have, and we'll talk a little bit about some solubility issues with this, and we'll dissect that. And they're found in a lot of pharmaceuticals. The aldehyde has at least one hydrogen, with our lowest, or our simplest one being formaldehyde, which has two hydrogens. Ketone has two alkyl or two aryl groups. Now, it can't be an OH, it can't be a chlorine, it can't be anything like that, because that's a different functional group, and we'll be focusing on that in later chapters. So it must be a carbon-containing group. Here are some relevant aldehydes and ketones. Some of these are natural, well, all of these are natural products. My favorite reaction to work with is benzaldehyde because it smells like almond. I really like almond flavoring. We worked with vanillin in the lab, so there's your vanilla flavor. And of course, that has a carbon oxygen that has an aldehyde. Sometimes now all of these are, of course, compounds. So cinnamon flavor is commonly called formaldehyde because it has that aldehyde. And that's often common names are named that way. But we'll talk about the IUPAC naming of a lot of these. And then, of course, we have a lot of ketones and aldehydes and natural hormones like progesterone and testosterone. So, of course, we got to talk about naming these. So, let's talk about our aldehydes first. Nomenclature of aldehydes. And I just emphasize al. Because that's how we're going to name it from the parent. So the parent name must include our carbonyl carbon, because at this point, this is our, of all the function groups we talked about, this is our most oxidized carbon. So we usually put our most oxidized carbon functional group in priority. Usually reactivity and oxidation is what we're thinking about. So typically these will be listed as our identifying parent name. For aldehydes, again, I just emphasized the al in aldehyde. We replace the E in our parent name with al. To represent, we have an aldehyde. That's where the al comes from. So our naming usually goes with functional group names. Then we identify our native substituents, side groups, and we put the locate number, and we always want our aldehyde to take priority, which means our aldehyde is going to be 1. Because our carbon of the aldehyde has to be at the end, otherwise it can have a hydrogen present. Also notice, oftentimes when we draw aldehydes, we do draw that hydrogen, because it's a special hydrogen. You don't necessarily have to, but I think it's very pleasing to draw it, because otherwise the C-oxygen double bond at the end doesn't look very, kind of looks weird. But it's commonly drawn, that hydrogen. That hydrogen is very specific. It comes out around 11 in the NMR, which is really the only thing that comes out there. So it's kind of special. It's often drawn. So if you don't necessarily have to. It's not necessarily wrong not to have it, but you will often see it drawn. Now remember, if you do draw it, you have to draw the H. Because if you don't, then it's part of it. Also, we do not count that in our parent numbering. We only count carbons. So the hydrogen's just hanging off. So our aldehyde is typically going to be our number 1 carbon. And then we assemble the name alphabetically. We choose the parent that has the most functional groups if that's a choice, all those things. So let's look at this example. Butane, once we put the aldehyde on there, it's butanol. Pretty straightforward. Also notice, we don't typically put a locate number Because it has to be 1. Because it's going to be our highest priority and it has to be a locant. So you will often not see a locant number with aldehyde parent names for the aldehyde. If we look at octane, depending on where our aldehyde is, that changes our longest chain. So because our longest carbon chain was 8, but it doesn't contain the aldehyde. So now our longest chain is going to, and that only makes it hexanide. Again, notice the number isn't necessarily there, but our propyl group would be on number 2. If we look at this one, we want to try to contain the carbon chain that has the most of these functional groups. It just makes it easier. So our parent should be this one because it also contains the double bond if we have that possibility, and the alcohol because, again, it just makes it easier to name. So we usually try to choose our parent as the longest. This one would also be as long, but then it would contain the double bond. So again, our carbon of our aldehyde is the highest oxidized carbon. So it's going to be number 1. So our parent is still heptanol, and it's still going to be number 1. Now we have a methyl side chain. Since we have the aldehyde, and we also have the double bond we have to name in the parent, the hydroxide is going to be a side chain. So it's going to be a hydroxyl, because it's easier to name that way, instead of being named for the parent. So remember, when OH is a side group, it's a hydroxy group. So then we just put this together alphabetically. H before M. Hydroxy dimethyl, we have 2 methyls, heptanol. Oh, sorry, heptene L. Notice this is an E for the E. So you do have to specify that. And then we're going to put the locant numbers. Now again, you often won't put the locant in front of the AL because it's understood to be 1. You can put it, but it's often not there. So that's going to be our number 1 because we want our carbon of the carbon-oxygen double bond to be the lowest possible. Then everything else just follows that. So we have 5 hydroxyl, 5, 6 dimethyl, and then 6 for where our double bond starts. Remember, for the double bond, we only specify the first number. You could also write it like this. You don't have to put the 6 right before the E. Also notice we're still naming it E, but we don't keep that second E, because then it would be EL, and that's not usually counted. Chirality is named the same way. You put it at the beginning of the name, no change there. In this case, because of the carbon-oxygen double bond not being directly attached to the ring, that's not a benzaldehyde. So in this case, our ring will be a substituent because our priority is going to be our carbon-oxygen double bond. So that's going to contain the parent. Yes?
So for all of our naming this semester, like all the functional groups have been as priority. If they have multiple functional groups in one molecule, like how do you know which ones?
Typically, the IUPAC agreed upon route is the most oxidized carbon. Now, if you have multiple oxidation, like chlorine versus OH, because that oxidation of that carbon is the same, OH is more reactive because it can act as a nucleophile, or that carbon can act as an electrophile. So then usually OH takes priority over things like halogens. However, once you start getting to the point of multiple functional groups, the IUPAC naming system does get muddy, and there are different ways you can name things. So if you look up a very complex molecule that has multiple functional groups, and you're trying to buy it somewhere, you often see, okay, here's the name, you look up, and then you also see also known as, and it'll list a different method for naming by the IUPAC that is also accepted. So it does get more muddy, which is why drugs are not typically sold under the IUPAC name, and instead typically sold under something like a trade name. Also, if they sell it under a trade name, then it doesn't necessarily tell you what the drug looks like. But oftentimes it's muddy. Brendan was talking in his talk yesterday with his RU program that he made this big molecule, a supramolecular, meaning a big organic compound. Supramolecular just means molecular, it's really big. And he's like, yeah, the actual IUPAC name of this is like 5 lines, and they have it on a shirt, and he's like, yeah, we just call it whatever, and we just gave it this weird name. So you got to realize how for the IUPAC, there's still going to be some muddiness. But for the most part, when I'm giving you these, I'm testing you on this, I want you to choose the carbon that's most oxidized as your priority name. So in this case, that's still what we're doing. And that is the most agreed upon route, but sometimes, and we'll especially see that when we start getting to carboxylic acid derivatives, well, you might have two carbons that have around the same oxidation state. So then you can really name it multiple ways and it's accepted. So it does get muddy the more complicated the compound gets. And I won't lie about that, it really does. I mean, they tried to come up with a systematic way, but the more functional groups, if you're trying to name something like progesterone with the IUPAC name, there's so much going on there, it's really difficult to do. So it's not always easy to name based on the IUPAC name. I'm not going to give you one that's really crazy. But if you're doing something like taking the MCAT, oftentimes what they like to do is ask you a question and they'll give you the questions with the compound's name instead of drawing out the synthesis. So I'll give you a starting material and I'll give you a box and you put the product. The MCAT might say react blah 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 with, and then you have to draw it out from the name and then figure out how it reacts, and then it might give you multiple choice of products drawn in skeletal structure. Or it might give you the starting material and skeletal structure and all your product names that you're choosing from is all an IUPAC name. So you do have to be able to do this. But when you're reading it, you can see ones that are more or less right. So I'm giving you the rules, and again, it can get muddy. It really can. I'm not going to lie about that. So here, the best way is to name our parent this and our benzene as our side chain, because if we named our benzene as a parent, it would be too complicated. So we want our most oxidized carbon, our aldehyde carbon, to be 1. So this is going to be R2-chloro, 3-phenyl, because when benzene is a side group, it's a phenyl. Propanol. And again, as soon as you see the Al, you know it's an aldehyde. And you'll often see that even in trade names, where the actual trade name has the Al somewhere in it. So that kind of represents that the functional group in that drug is an aldehyde. Now there is one thing that you do need to recognize, and that is when an aldehyde is directly bonded to a ring, then the parent name becomes carbaldehyde. Because you really don't want your parent to be methaldehyde. That's what it would be, with this being cyclopropyl. So instead, this is a carbaldehyde, but it's only when the aldehyde is directly bonded to a ring. Now, if that's a benzene ring, it's benzaldehyde. But if it's anything else, it's a carbaldehyde, and then you just name whatever ring it is before that name, carbaldehyde. So if you see the term carbaldehyde, it's a ring with a aldehyde directly attached. So in this case, it would be cyclohexane carbaldehyde. Because you do have to specify what size. If there's any functional groups attached, you would just put that, and this would be your number 1 carbon, because the parent is named for that aldehyde. This is only a name when the aldehyde is directly attached to a ring. If it's not directly attached to the ring, you're not using carbaldehyde. So looking at this example, our parent is pretty straightforward. Remember, don't count the chlorine, that's not a carbon. So this is a hex. We do have an ene at 2, so this is a 2-hexene all, because we want that aldehyde to be number 1. And then of course we have 6-chloro. And we do have a double bond, and it is not, we can't rotate it. So we do have an E or an a Z isomer. So in this case, this is the E isomer. Our 2 largest groups are opposite to each other. This is our highest priority on this side. This is our highest priority on this side. So that means opposite in German. Well, E doesn't mean opposite in German. The word comes from it. It's opposite in German. I think it's in Tagen. I'm not really sure how to pronounce it. I really need to ask my friend. I have a friend who is from Germany, and I never asked her the correct way to pronounce that word. I need to call her. She's working on drug synthesis in Boston, at a small startup pharmaceutical company. And her dad was the main chemist at Merck on therapy. and he came talk to us for once. He's retired now. Really good retirement package. Side note, I find it really interesting. She's from Germany, and they moved them down here to work on that particular compound from here. So that's our aldehydes. There are some common names we need to recognize. Formaldehyde, of course. That's typically how formaldehyde is represented, not based on the IUPAC name. Acetaldehyde. So the ACE term, again, you commonly see it when your CH3 is directly bonded to a carbonyl carbon. So you see acetic acid when this is an OH. We see acetone when this is a CH3. So acetaldehyde is when this is the aldehyde with ACE. So you see that ACE a lot. So that's typically what the ACE means, is that you have acetaldehyde with the carbon directly attached. So it's just ACE and then the aldehyde. Well, the ACE stands for acetyl. So that's why that T is there. And then, of course, benzaldehyde, we already know that one. That's a benzene ring with the aldehyde directly attached. We've looked at that one before. So really, it's just acetaldehyde that's new to you. Oh, and guess what? Thanksgiving break is in 2 weeks. Isn't that exciting? I'm excited. I know I don't. So, in the next 10 minutes, I'm going to go through naming ketones. Well, I'll introduce naming ketones, and we'll really get into it in the next class. So, unlike aldehydes, ketones can be anywhere in the compound, but because it was at the end, and it's at my aldehyde. So we do have to specify the locus number for these, because it's not just going to be one, because they can be anywhere. But it's still going to be our highest priority, because it's our most oxidized carbon. So for ketones, we're going to replace the E with O. That's pretty easy. Ketones in the name, so we replace that with O. But we do have to have a locus number in these cases. We then identify our substituents, then we number them, making our ketone carbon the lowest number possible, taking priority over other functional groups. And of course, the locus number can be either before the ohm or before the penny. So fairly straightforward. Then assembling alphabetically. So instead of butane, this would be butanone. And in the case of butanone, which is really the only one, we don't really need a locus number because whether the ketone is here or here, it's still butanone because it's symmetric. But every other compound we have to specify. You can still specify it as 2-butanone, but that's the only possibility of that being a ketone. Because if it's on the end carbons, it's an aldehyde. Yeah.
So when it's a ketone, even though it's a different functional group, you still count the carbons in the ketone.
You want the carbon of the ketone to be part of your parent. So if it's not part of your parent, then it's not taking priority. So by it taking priority, you want it to be part of your parent chain.
Yeah, so like instead of like with the aldehyde where you didn't count it.
You counted that carbon of the aldehyde, that was 1.
Yeah.
But this isn't going to be 1 because ketone's never going to be at the end because it has that 2 R groups attached. So that's why you have to specify the locus number. But you're always starting with a linear compound at an end carbon. In a cyclic compound, you're going to just call it ketone. But in a linear, you always have to start your numbering at an end carbon. So then, based on that, you want your ketone carbon to be the lowest number possible. So for example here, we want our ketone to be 3, and then we can write 3-heptanone or heptane free, no ohm. Also notice the E is dropped from heptane. That's pretty common because we have an ohm here. So it wouldn't be 5. It would be, we want the lowest number in the system possible. There are some common names that you need to recognize. Again, that ACE group is at CH3. So when we have two CH3s, that's an acetone. It also could be propanone, but it's more commonly called acetone. And we use that all the time in the lab. Here's just what it looks like. It has a very low volume. Then acetophenone is the benzene ring with the ketone with the CH3 group. And if you were naming other substituents on the benzene ring, the parent would just be acetophenone. And then benzophenone is when you have the ketone and the two R groups or benzene rings. Now, as soon as there is a CH2 group that is separating the benzene from this, it's no longer benzophenone. So this is a specific compound. It has to be your two benzenes are directly attached to this ketone carbon. You can also name it very similar as to how we did the, and this is accepted by IUPAC, but it's rarely used, mostly because ketones are usually in compounds that are more complicated. But remember how we named our ethers, or we could name alkyl ether, like our dialkyl ether. We can also use that same naming system for the ketone, but it's not used very much because as soon as you have any functionality, it gets too complicated. But technically, this could be methylpropyl ketone, and you're not including the carbon. So that is a route you can, but anything more complicated than something really simple, it's not used, so you don't see it that often. But you might come across it, so just be aware of it. So sometimes, again, this is a case where you might try to buy this compound, and you would see it as 2-pentanone, or you might also see it also known as methylpropyl ketone. So you might see that. So we'll actually go through and name this one. Notice this one has 2 ketones, so we'll talk about that. It also has multiple functional groups. So we'll look at some examples in the next class on Friday. I also want to point out we finished a whole chapter. Just pointing that out. Yep. Finished the electrophilic substitutions of the aromatic ring chapters. I'm just saying.